Good morning. I am Dr. Fatima from SIRT. Today's lecture topic is AC bridge. Now, the bridge circuit actually it operates on the principle of the comparison. That is, some known value or the standard value is adjusted until it is equal to the unknown value. So, on the basis of this principle, the bridges are used for the measurement of Wheatstone bridge, for the measurement of resistance, and for the measurement of inductor value, capacitor value, and frequency. The DC bridge and AC bridges are the type of the bridge circuit. The DC bridge is used for the measurement of resistance only, and AC bridge is used for the measurement of inductor, capacitor, and frequency value. The DC bridge classification are Wheatstone bridge, Kelvin bridge, and Megom bridge, double Kelvin bridge. The AC bridges, for the AC bridges for the measurement of inductor, Maxwell bridge, Hayes bridge, Owen bridge are used. For the measurement of capacitance, sharing bridge is used. For the measurement of frequency, Wien bridge is used. Now the capacitor, actually the capacitor, if I'm talking about the capacitance, it means that this is the ability of a dielectric to store the electrical charge per unit voltage. So you can see here, this diagram is showing a parallel capacitor. The two plates of the conductor in between dielectric is present. The plate is having some area A and the distance between two, let it be denoted by D. So the formula for the parallel capacitor C equal to epsilon A upon D. That is, the epsilon is epsilon R and epsilon. So epsilon R is the relative permittivity of the capacitor. Epsilon is the permittivity of the free space, and A is the area of the plates, and D is the distance between the two plates. This is the equivalent diagram of the capacitor. In the capacitor, the resistance comes here in parallel and inductor is also present. The typical values of the capacitors are microfarad, nanofarad, and picofarads. Next is the inductor. The inductance, actually this is the ability of a conductor to produce induced voltage when the current varies through it. So you can see that in the diagram, there is a core on which the wire is wounded. L is taken as the length of this wire, and if N is the number of turns, and if I'm saying mu R is the relative permeability of the core, and mu naught is the permittivity of the free space, then the inductor or inductance capital L can be given by mu naught mu R N square A upon L, where L is the length of the wire, A is the area of the wire, N is the number of turns, mu naught is permeability of free space, and mu R is relative permeability of the core material. This is the equivalent diagram where the inductor is connected in series of the resistance. Some resistance is present in inductor. A stray capacitance or the distributed capacitance is also appearing between the two turns as shown in this diagram. This is one conductor, this is another conductor, and air is present between these two. So this is showing a distributed capacitance or stray capacitance. This comes in the picture, although this is not connected. So you can see here, this is the air core inductor. This is the symbol of the air core inductor, and this is the iron core inductor. Here, this is the symbol of the iron core inductor. The quality factor of the inductor and the capacitor. The quality factor of the inductor, if the resistance is connected in series, then this is given by omega XS upon RS. That is the reactance of the inductor divided by resistance. That is omega LS upon RS. Omega L is the reactance of the inductor. If the inductance is in parallel, if the resistance connected in parallel of the inductor, then the quality factor is given by R divided by X. This RP is representing the parallel capacitor and XP is representing the parallel reactance of the inductor. P is denoted here for the parallel. X is the reactance of the inductor and R is the resistance of the inductor. So this is equal to how much? Rp upon xp is equal to omega L. X is equal to omega L. That's why I can write xp equal to omega Lp. So the inductance parallel circuit quality factor is equal to Rp upon omega Lp. The next is the dissipation factor of the capacitor. This is the ratio of the reactance to the resistance. Same as the quality factor I'm talking about for the inductor. Now this dissipation factor, this for the parallel combination of capacitor and resistance, this is equal to the reactance divided by resistance. Since here the parallel combination is taken, so P is used as subscript, so I can write here XP upon RP. The value of X is equal to 1 upon omega C. So value of XP is equal to 1 upon omega Cp. Rp is already in the denominator, so that's why the dissipation factor of a capacitor is equal to 1 upon omega Cp Rp. Now, if the capacitor is connected in series of the resistance, then this dissipation factor will be equal to resistance upon reactance of the capacitor. Since the capacitor and the resistance are in series, here the S is taken as subscript. So this is equal to Rs upon Xs. The value of X is 1 upon omega C, and if I'm writing for the Xs, the value of this Xs is equal to 1 upon omega Cs. So I'm substituting the value of Xs here. So this is equal to 1 upon omega Cs, and it becomes this dissipation factor of the capacitance series circuit is equal to omega Cs Rs. So this much about the quality factor and the dissipation factor of the inductor and capacitor. The importance of the quality factor is if the value of this capacitor is very high, if the resistance is 0, then the value of this quality factor will be very high. It means the resistance is 0, that is the inductor is pure. There is no resistance present inside of the inductor. So the quality factor is very high. So we always prefer to take the inductor with high quality factor. If the quality factor is very low, it means the very high value of resistance is present. So the low quality factor resistance inductance are not desirable if the inductor comes in series with resistance, and vice versa with the inductance parallel circuit. So the quality factor and the dissipation factor decided the quality of the capacitor and the resistance, or you can say the value of the resistance present in inductor and capacitance. Now come to the Wheatstone bridge. This Wheatstone bridge is used for the measurement of resistance. Here the resistances are connected in the 4 arms, the R1, R2, R3 and R4. So the R2, R3 and R4, these values are known, and unknown value of the resistance is connected in this arm, arm A, D. Between arm A and C, the DC voltage supply is connected, and between arm B and D, a galvanometer is connected. The galvanometer is connected to check whether the bridge is in balance condition or not. Now, what is the balance condition? The balance condition means the potential difference across this galvanometer must be 0. Or we can say that the current should not be flow through this galvanometer. If the current does not flow through the galvanometer, then the bridge is in balance condition. Then we can apply this condition, R1 upon R3 equal to R2 upon R4. That is, the product of opposite arms are equal. So the first pair of the opposite arm is R1 and R4. The another pair of the opposite arm is R2 and R3. So R1, R4, this product must be equal to R2 and R3. So this is the balance condition for the DC bridge. Wheatstone bridge is DC bridge, and it is used for the measurement of resistance. So by knowing these values, the resistance R1 can be calculated by applying the balance condition. Similarly, for the AC bridges, the AC bridge is also having the impedances in 4 arms. But this bridge is used for the measurement of inductor and capacitor value with the help of the balance condition. Now here the impedances are connected in the 4 arms, Z1, Z2, Z3 and Z4. Between the point B and D, the AC voltage supply, AC supply is connected, and between the arm A and C, the detector or the galvanometer is connected. If I'm saying the bridge is in balance condition, it means the voltage drop across this detector or the galvanometer is 0. It means the current will not be flowing through the detector or the galvanometer. If this is so, then the bridge is in balance condition. So I can apply the balance condition. A balance condition is the product of the opposite arm must be equal. So the opposite arm, first pair of opposite arm is Z1, Z4, and another pair of opposite arm is Z2, Z3. So this must be equal. The product of opposite arms of impedance must be equal. That is Z1, Z4 must be equal to Z2, Z3. But in the AC bridge, this is this Z1, Z4 equal to Z2, Z3 is not a sufficient condition for the balance. Since here the impedances depends on the frequency, so the angle also appear in the picture. So Z1, Z4 equal to Z2, Z3. This is only the balance condition. This is only the one balance condition. This is called magnitude balance condition. And for this, the another balance condition is phase balance condition. That is the phase angles of impedance Z1, Z4, and phase angle of impedance Z2 and Z3. The addition of these two must be also equal. That is, angle theta 1 plus angle theta 4 must be equal to angle theta 2 plus angle theta 3. So if this bridge satisfy these two conditions, Z1, Z4 equal to Z2, Z3, and theta 1 plus theta 4 equal to Z2 plus Z3, then we can say the bridge is in balance condition. And these balance conditions, if the bridge is at balance, with the help of this, the value of unknown inductor and capacitor or unknown impedances can be calculated. So this completes this lecture.